Malsinski.
And I will pass it off. I'll pass it off to Jake. We'll go back and forth a little bit.
Very good. This presentation is, I think, targeted on New Mexico's decarbonization efforts as well as water. I think a little bit on water as well.
Yes.
Very good. So I won't try to say any more than that. And Len, I will turn it to you.
I just want to say hi to Will. I don't think I've seen him since 2016, maybe.
That could be. 2016 was also Delft, I think, right?
The last conference in Delft.
Yeah, that's right. That's right.
Okay, here we go. Here we go. So, as Joe said, this is about two projects. One we're calling Modeling Decarbonization, which in short we say is heavy in stakeholder engagement and a complex model, which we hope would lead to understanding. And then the produced water model, which is also a complex model with a very sophisticated interface, and it leads more to decision scoping instead of understanding. Let's just get into this. I'm going to go quickly, and Joe will work out a way to provide the slides as a PDF later.
Very good.
So the official title of this project was Stakeholder-Driven Energy Storage and Decarbonization Modeling for New Mexico. Lots of text. I don't expect you to read it.
Then we can't see your screen.
I'm not sharing? I thought I was sharing. Maybe not. Okay, here we go. See that now?
Yes.
Yeah. Okay. So the state of New Mexico, like most states, most people around the world, are worried about decarbonization, whether we can reach the goal or not. The Department of Energy in Washington, D.C. has a strong relationship with Sandia National Laboratories here in New Mexico, and they asked them to start a project looking at decarbonization in this state. The thing that made this project relatively unique, let me grab a pointer, was the fact that we got the Public Regulatory Commission, the New Mexico Energy, Minerals, and Natural Resources Department, that's part of the government. This is an independent body, and the largest public utility in the state to work together. Go forward here. I'm just going to, because you'll get these, but people were interested in what are the most important uncertainties about this future. DOE's Office of Energy Storage funded some of it, so they were very concerned about storage inclusive portfolios. And then finally, the state of New Mexico Energy, Minerals, and Natural Resources Department, which we call MNERD, was very interested in trade-offs, especially environmental trade-offs. So here again, a review of the stakeholders. Here's the sponsor. Sandia National Laboratories led the effort. The primary investigator was there. They hired us, Mind's Eye Computing, and then we had a management and technical writer from a small company called Bosque Advisors. And I don't know, at any one time, we might have had 10 people in our stakeholder meetings. Again, repeat maybe. What are the alternative scenarios? Now, not all of you live in a state that's organized like ours, but the public utility here must present a 20-year plan of all their electricity generation ideas. Every 3 years, they have to issue a new plan. Then the Public Regulatory Commission looks at that plan and either approves or disapproves or asks for changes. So what are the scenarios? it turns out P&M had 75 scenarios, which are quite difficult to manage in your mind, as you'll see when Jake brings up the model. What resource portfolios would you like to explore? Are you a photovoltaics person, a wind person, a battery storage person, a hydrogen person, coal, natural gas, nuclear, hydro, geothermal? What kind of mix do you like? What are the trade-offs that you think are important, right? Every time you make one choice, you give up something else. What are those trade-offs? And of course, the burden on Jake and I, could the interface on the model provide an adequate understanding of what's going on? So we met for regularly scheduled meetings with representatives from all the stakeholders. The least active person was the public utility. So the first half we met literally weekly. Every week we had a meeting with the stakeholders. We also had a weekly meeting with the modeling team. For the second half, we fell back to bi-weekly, and we had lots of ad hoc meetings. Whenever there was an issue about data or presentation or inclusion of a certain variable, we got on the internet and started a Zoom meeting and got an answer. We had several long-term in-person workshops, several hours, drove up to Santa Fe where the state government here is housed, did a meeting here in North Albuquerque. And I just wanted to highlight this. I mean, when I look at the crowd here, I think you all know this, but we could not have completed this project without the very diligent and dedicated participation of the stakeholders. Right. Here's a little bit about the modeling details. Sandia Labs had 4 staff that interacted with the model, but intermittently. In fact, one of them retired from the laboratory about a quarter of the way into the project, and the PI retired last week. Mind's Eye, there are only 2 of us, Jake and I. We developed it in an MS Windows platform with PowerSim Studio and Excel. The model itself has 1,200 variables. To me, this is important. There are about 140,000 individual values in the model. So the phrase I came up with the other day is detail ratio. I just divide the number of elements by the number of variables. So it's heavily arrayed or subscripted if you're a Vensim person, right? 70 stocks, constants, auxiliaries. We also do sub-modeling, sort of reusable components. And because it's detailed to the electric industry, there are 37 different kinds of units in the model. Go forward. Jake, it's all yours. I'll stop the share.
Okay. I get to do the fun part. So this is the introduction screen. I'm assuming everybody can see my screen now. Yes? Okay, good. So in the introductory screen, we got pictures, but it's all, button driven. We have to start out because we, DOE and Sandia require a deniability. So you can do things with this model that may not be physically possible, but you can model it. So you accept those responsibilities. This is some discussion pages on introductions to it. We'll go through the model, so we won't worry about this much. This is sort of the main driven interface screen. And what we have are our scenarios where you set up different options of what you want to look at. You can work with the load. So what is the demand on the electricity market going to be, and how are you satisfying that? What is your resources that you use to satisfy it? And then we look at the results, right? What are the trade-offs and what are the values that come out of that? So we really break it into 3 different sections. For scenarios, what we do is we looked at, we really didn't get into population and energy intensity, but we could do that. What if the population exploded or dropped off? What would the demand do? We did look heavily at EV adoption. And so what would the adoption rate be, and what would the impact be on load? And then we had some policy work. So we spent a lot of time working on these policies, and these were really stakeholder driven. This is what the stakeholders were interested in. Behind the meter PV, building electrification, what would that do to load? Time of use settings, right? New Mexico does not right now have a real strong time of use policies, and they were looking at that. They also wanted to look at what if we just did time of use for electric vehicles. And so that's our policies. Then we also look at the load. So this model runs on monthly time steps. And what we did to be able to model the market is we modeled a average 24-hour period for each month of the year. So we take, and this is our 24-hour graph, the load over a 24-hour period for a month, and this is January 2021. This data came from PNM. PNM is the utility company. They shared immense amount of data with us. I mean, like a gigabyte. So we had half-hour data for 25 years on their predictions. So we were able to take that and gen it down into what we needed for this model. But they were very good about sharing the information that they had in their predictions for what they think the future is to be. And this is their load profiles out for 25 years. So you can see the peaks and demands of the annually for highs in the summers and lows in the winters and that. And so what you could do, and then they also gave us their estimated transmission and distribution losses, what you lose through the transmission line. So, and so as we step forward with the model, you can see how that load curve changes from month to month to month. So some months have low peaks and high peaks in the evening hours, and that changes every month of the year. And then this changes annually because you have annual growth, right? Yeah. So we're able to track that and do that. So what we did was we took their base case and we modeled it, and that allowed us to calibrate to their case, and it allowed us to check how we distributed our generation matched how they were doing theirs. And they do their generation at 15-minute intervals. So they're filling out their demand at 15-minute intervals. We're doing it at a kind of an average at a monthly scale on an average 24-hour period. So what we had to do is be able to calibrate our dispatch calculations to what they were doing and be close enough that we got relatively good, consistent results with them. And we were able to do that. It took about 8 months of hard programming and working with PNM to be able to do it, but we were able to accomplish that. So that's the load. Then our resource portfolio, we have a whole series of generations. And these are the generations systems that PNM is working with. So they have coal, nuclear, natural gas, geothermal, solar, and wind. And those are the ones that they see happening in the near future, right? So in their coal profile, this is what they see coal doing. And they're going to have it. They are heavily into coal right now, but they expect coal to be offline by 2024. And so this shows you that profile. This is their nuclear, and they get nuclear power out of the Arizona nuclear power plant down there, Palo Verdes. And they're going to lose some of their nuclear power in 2023, and then they're going to be stable the rest of the time. The fight between nuclear is not considered renewable, but it is. I just saw the other day that it is now considered to be, I call it a green technology. So, so then they also have natural gas, and they have, we broke natural gas into combustion turbine, combined cycle, and hydrogen ready. And we broke them up because they're handled differently. Combustion turbine typically handles peak demands. So they're peaking machines. So where combined cycles are more in lines for base load. And that means that they try to run combustion or combined cycle kind of steady without a lot of ups and downs, whereas combustion turbine, it's really designed so it can go up and down fairly easily and make peak lines. So, and hydrogen ready, these are new turbines that they're developing that can be converted to hydrogen for their energy instead of gas in the future. So they start out using gas until 2040 when hydrogen. And then they do have a little bit of geothermal that they use. And this is their predicted solar that they're seeing. And this is industrial solar. This is not rooftop solar. This is looking at what's coming on their solar sites. So you can see there's a big jump early, and then there's not a whole lot of PV coming online until the magic year 2040, which is when New Mexico goes totally carbon free on their grid. So you can see magic happens in 2040, and they get a huge jump. Wind, they have a pretty good supply of wind right now. You don't see much wind come online until 2032, and then not that much. And the reasoning behind this is that they have a real restriction on transmission. It's very expensive and very time consuming to build new transmission lines. So where PV, you can build them anywhere, you have solar, where you have sunlight. Wind has to be, in a good wind area. Those wind areas are restricted by the amount of transmission available. So it's a really good source of energy because it blows, 24 hours a day a lot of times. But unfortunately, it also requires that you build extra transmission lines. So that's what it looks like for generation. We also managed, because we were being funded by the storage group at U.S. Department of Energy. So we managed, we modeled battery storage, and they brought 4-hour battery storage on early. You don't see 10-hour battery storage till later. So, and that's really a matter of when they're coming in the development stage. So, and then we did manage also to model hydrogen, and they see hydrogen, PNM sees hydrogen not till 2040. So they don't see that coming on very early. So those are the generations. So, and a user can change these.
Jay,
Yes.
Does New Mexico have much imported electric from adjacent states?
They do a little bit. They do a little bit of trading between them and Texas and Arizona, but it kind of balances. So they'll do a little importing in this time, but mostly it's a balanced system on that. So,
and those generation portfolios, I assume, aren't very different than what you just showed.
Correct. And what they do have, and what we're not modeling is they do send a lot of electricity to California, but that's actually by a different group. And so we're not modeling that at all, because that's generated wind or PV in the state, and it's all shipped out. So we're not counting any of that. This is only stuff that's generated and used within the state.
So in the state, there's actually more production via renewable, but it's being exported.
Absolutely. Yeah, they're a great wind area. So they have a lot of wind that's going out of state. And those companies that do that, they have actually built their own transmission lines for exporting it out of state. So
they have found the sweet spots and they're using it for export.
Absolutely. So you'll see that in a lot of different states. Like Wyoming is a huge, sweet spot for coal. And I saw one time years ago that Wyoming per capita used more energy than anybody else, because they were including the energy developed in these coal facilities that were being shipped out of state for being used within the state. So you have to be careful how you do your accounting. But so anyway, what we wanted to be able to do is look at these, the default base case that PNM has, and then kind of tweak it and see what happens if we change different parameters. So this is a kind of our main output screen we look at. And you can't really see it, but there's a red line at the top of this. This is the demand. This is the demand for electricity. So this is the load that's out there. And these show you what is meeting that load. So red is nuclear. So nuclear likes to run full out. They don't like to tweak nuclear up and down. So it's what we call a must-run generation. So you don't change it, you don't fluctuate it, you just let it run flat out. So you see nuclear flat for a 24-hour period. And so it's supplying that. The black you see here is being supplied by coal, the blue by wind, and that yellow you see is when PV is online, so when the sun is up. And so we can step this through. So this is for January 2021. And you can step it through and you can start to see how that profile changes and who's supplying what when during these different months. And you can see there's a little bit of yellow above the red. And this is PV that's being supplied that you can't put anywhere. You don't have any use for it right now. So it's excess PV. So you would have to kick that offline and not use that. So that's PV that you'd like to figure out a use for, but right now you just have to truncate it. So the neat thing is you can walk this through and see these changes for every month of the year for the profile that you have. So I'm going to go ahead and run this out to the end of the run. And we have 3 different values that we're tracking on this screen. And this is kind of a cost value. What is the amount of money that is costing to run this system? What are the CO2 emissions, right? This is the important part of what they're trying to reduce. Oh, for God's sakes, let me start over. I got to reset. We reset everything. Now run
That
it.
looks like a great deal of curtailment of the PV panels. Is there storage to, is there sufficient storage to capture that curtailment?
No, because storage is so expensive and it's actually not really going to come online till much later in the years too. So, but storage is still very expensive. So it's still not a real huge impact. So what you want to do is you want to bring on enough PV in the really starving months that you can fill your batteries and that. You don't want to have so much extra PV that you just start throwing it away. So it's a balance, right? It's a real balance between it. So this is our reference case that P&M kind of lays out as their baseline. This is what they're shooting for. And you can see that they've got a net present value, CO2 emissions, and a very low unserved load. And so what we do is, what we've been doing in these meetings is we start out with this profile, and it looks at it. It has that generation profile that I showed you, the coal going offline in 2024 and all those other profiles. But the big question we got when we came into these meetings was, what would happen if we had a really high EV adoption? What would that do to my demand, and would I be able to satisfy it with my current set of generation profiles that I have online? So I'm going to really increase EV about 5 times more than it is in the default base case. And I'm going to run this forward just a little bit, and I'm going to pause it. You can see the green line is just slightly above the red line. And so you're seeing the adoption start to come in, and you're seeing load start to increase. And you see load more, a larger difference in the evening hours, because most people come home and they plug their EVs in when they get home. So you see these evening hours, the load being higher than in the morning hours. So as you go farther along in time, you can see that the EV adoption is starting to grow and grow, and we're getting more EV cars, and we're getting more and more demand. So this is playing out to what we think. So what is the impact of this? So if we go out to the year 2045, you can see that I have a higher cost. That's because I'm having to run my generators more, my combined cycles and combustion turbines more. I have a much higher carbon emissions, and I have a ton of unserved load. So this is a measure of how the quality is of the system. This tells me the system is not going to be able to adequately supply the customers in the time they need. So it tells me that the generation profile we have will not meet the needs if we have a really high EV adoption. So the solution that the committee, the PRC says is, well, we want a ton of solar anyway, so let's add more solar to the system. So I'm going to save this case so we can use it as a reference, and I'm going to call it a high EV adoption. And what I can do is I can change these reference cases over here. So this is the base case. I'm going to change it to my high EV adoption rate. Now you can see they're equal. But now I'm going to reset. I'm going to stay with the high EV adoption rate. But now I'm going to come down to generation, and I'm going to increase the amount of PV, amount of solar that's online, that I want to bring online. And so I'm going to manually say that's the amount of EV I want. I want to bring on a lot of EV. And then I'm going to run this and go back to my trade-off screen. And I'm going to compare it against just my high EV adoption and see if I fix the problem by bringing on a bunch of PV. And what you see is I did reduce my carbon, and I'm still a little bit more expensive, but not a whole lot, but I reduced it by 1/3, but I still have a high amount of unserved load. So just bringing on PV didn't solve my problem. And the reason for that is because we have a mismatch. We have people charging their EV vehicles in the early morning and late evenings, and that's not when the sun's burning. So without some kind of storage, you just have this excess EV that's just not being used. So, so the thing is well, why don't we add battery storage? And I'm going to save this case. I'm going to save it as high EV and PV option. And then I'm going to reset. And I'm going to stay with the high EV adoption. I'm going to go back down to generation. I'm going to increase PV again. But now I'm going to go down to storage. And I'm going to increase battery storage also to a high level. And then I'm going to run it, and I'm going to check to see how well I've done in my metrics to see if I've satisfied everybody and made it all. So I run it. You can see who's supplying what when, and you can see now I've added a lot of cost to the system. Adding batteries and PV system has really upped the cost. I've really reduced my CO2 emissions, and I have a high low EV, but or unserved load. It's a lot higher than the case, but it's a lot lower than the high EV adoption. It's quite a bit lower than my high EV PV adoption, but as you can see, it's still, wrong button. It's still pretty high above my reference case. So there's my reference and there and that. So I'm still way high. So, and this is the kind of discussions we got into with this group. And you know, the original assumption from the PRC was, if we throw a bunch of PV on the system, we're going to be able to handle everything. Well, that's not necessarily true. So what they came to the realization is there's not a silver bullet, right? It isn't just PV. It isn't just wind. It's a combination. And then you have to start looking for these sweet spots. What is the combination? And it was pretty cool to watch with this committee because you got to see the PRC, which, you know, is a regulatory part of this, working with the utility company saying, you know, is this correct? Is this what you see? And the utility company goes, yep, this is about what we see. And we have real hard problems, you know, manipulating this and balancing these. And, you know, we don't want the cost to be extreme, yet we don't want to see a lot of unserved load. So what's that combination? So this model brought this three unique customer groups together that during this time we were doing this modeling, or actually the state of New Mexico was in a lawsuit against PNM. So we had periods of time where we couldn't even get them together in the same room because of the legalities of all this. So, but the PRC loved the model. They enjoyed using it. They called extra meetings to just have us work this with us. PNM actually wanted to use this in some of their open sessions with the public to kind of educate the public that is screaming for, you know, more PV. You know, that would solve everybody's problems. It'd be cheap and everybody would be happy. And so this worked out to be a really neat little tool for educating people on how this pretty dang complicated system works. So, and we've got tons of different metrics that we look at. We've got costs into the system. We've got how much curtailment of PV is going on, how much wind, you know, lots of different summary data that we look at. So, but the main idea is people love to work with this screen and look at how things are, you know, being served up and how much curtailment is happening, right? In this case, you know, I didn't tell you this, but in this case, you can see we have nuclear serving this up, we have batteries, and then we have wind. And then in this case, this is not a dull yellow now, it's a green. That's because that's being totally used. All that excess PV is being totally used for 4-hour battery storage. And so you're using that excess PV now. Now it's not being discarded. It's actually being used in the system. So you want to balance that PV, not having too much, with how much you can use for your battery storage and stuff. So, but a pretty cool tool. So with that, I'll send it back to Lynn.
Okay. I'll take over the share screen. So we did a little reflection. I mean, when I look at the crowd that's here today, most of you know that everybody always wants more, right? They want the model to do more. They want it to do differently. What made this model useful at all? Okay, information presented in a user-friendly way. No one really had a good way to describe the complexity of electricity delivery. It, included information from the utility, which is called the Integrated Resource Plan. It gave users the ability to alter that plan if they wanted to. They could see the trade-offs. They could learn something about the intricacies of providing electricity to more than 500,000 customers. And the calculations were all vetted by industry experts. So, you don't want to read this probably, but it introduced people to the uncertainties, problems with their mental models, etc., gave them the parameter values for trade-offs, and we thought was really cool bringing three diverse stakeholder groups together that typically don't interact in this way. They're typically adversarial. Let me go to the next one. Insights. Again, I'm preaching to the choir here. Stakeholder management involves time and patience, and I probably should have said money. I was joking with Jake about a George Harrison song about that: time, patience, and money. Once a feature is accepted, the next feature becomes paramount. So during this, multi-month period, you say, yep, we got that in the model, and immediately they have accepted that. Okay, where's the next feature? Why isn't it in there yet? Right? It's doing all of this was non-trivial, both in design and creativity. We've got a lot of experience in designing these so-called flight simulators, and the way we lay them out, the color schemes, all of that was up for grabs. So that's non-trivial. This is something that definitely hurt us near the end of the project. We did have a clear statement of objectives at the beginning to defend our work, but we were attacked very heavily for about the last 6 months of the project by the optimizers. The people who said, well, your model really should be optimizing the future on a 15-minute interval for the next 25 years. And, being a system dynamicist, I just come back and say, so you know what the future is, huh? You know what the future is going to be, so you're going to optimize your system to meet this make-believe future of yours. And we can do it too. And then there were lots of disagreements about our dispatch algorithm, which basically says, what electricity generation source do you need at each time of the day in your average day per month, and in what order do they come online? Most of the industry people use optimization. We proved to them that our relatively simple algebra yielded just as good a result as their optimization models, which literally can take days to run. As far as I know, we haven't spent a day yet on this. Oh, someone, let's see. Atika has a question. Shows data from 2021. Yeah, 1 year of data, but it was data provided to us in what, 15-minute intervals, Jake?
Yeah, it was 15-minute intervals, but we aggregated it.
We aggregated, because we definitely didn't want to run this model with a 15-minute DT, right? Let me go forward. We could take questions here.
Is it safe to say that 2021 is back to life as usual post-pandemic for the most part?
Yeah, well, that's hard to say in terms of electricity generation. It might be a little higher. I don't know if, how well people, how efficient firms were when their staff were not in the building. I mean, I remember at Sandia Labs, every Christmas we shut down between Christmas and New Year. And I was in a building where someone forgot to leave the heat on. And water pipes burst, and we had a mess. So I really don't know, Joe. But I'm going to go forward and start on the next one because we want to spend less time on the interface here.
Should we see if there's any questions? Just
Sure, sure.
any further?
Will.
Look for one from Will.
Yeah, I like the work and I like the comment on this is not optimization. It's playing with trade-offs and alternatives. And I'm not a specialist, but I'm following what's happening here in the Netherlands. And there's two things that I didn't hear of, or at least one I heard of, that is transmission capacity. And that's a big problem here. And there is huge pressure now, huge need to work on that. But maybe the situation here is totally different from New Mexico. And the other thing that I didn't hear of is the idea to use a surplus PV for hydrogen conversion. And also that's a long-term thing, but there is serious work on that going on here.
Yeah, so we do use the excess, after 2040, we do use excess PV in a hierarchy. First, it charges 4-hour batteries, then it charges 10 hours. And when it has excess above that, it charges hydrogen.
Okay.
So we do use it. And so we do have green hydrogen. Any hydrogen that comes on the system is green hydrogen.
Okay.
From PV, so.
Yeah, that's where it is. Yeah.
And we actually put transmission out of the scope.
Yeah.
Obviously, it's important, but we literally pushed it out of the scope for this version of the work.
Yeah, well, you have to make choices.
Yeah, it's hard, really hard.
No, and another thing, at least when I heard you starting to talk about the complexity of the model, I thought, oh, is this going to be transparent? But in fact, in your reflection, you also noted that it's basically accounting
Yes.
of all the different things, which makes it transparent if you can explain what happens. So it's not complex dynamics like in some other system dynamics models.
Yes, it's interesting how the user sort of becomes a part of the model.
Yeah.
Right.
Yeah.
And that's what flight simulators do, I think.
Then does the model have the ability to include behind the meter solar and battery?
We would like to, yeah, it does have some, and Jake had I don't know if we want to show that now, but Jake had a schematic, a sort of an org chart where we scoped out everything we wanted, and some of the boxes are in a different color because we never got to those. We ran out of time and money, basically, and then of course we had that attack. Go back
so
to
one of the
home screen.
policies we did look at was behind the meter. So we did a very simple behind the meter, just looked at adoption rate of behind the meter and how that was behind the meter PV, and then also building electrification. So we looked at these, but pretty much from a cursory level, just what it do to load impact. So
Jake, can you click on this? Can you click on the scope icon there in the upper right? You know where that little icon is under the play buttons? Yeah,
no.
Right there. You're right there. Go to your right. No, go to your right. Up, 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 up. Nope, down. The icon's right there. Yeah. So you can see the stuff that's grayed out we never got to. When we did the first stakeholder meetings, we did the typical group model building. What would you like to see? What's important? And we didn't get to some regulatory stuff, some natural resource and climate stuff. I can't read this right now. Let's see, there's a question from Warren. EVs is incorporated as a supply. Sorry, not as a supply. We didn't get that far. It's just load.
Yes.
There's no contribution back in parking lots or anything like that yet.
Yeah, we had a lot of discussion about using them as a source, but PNM was not in the position that they wanted to talk about that because of the complexity it adds to the grid management. So.
Okay, should we go on to show a little bit of the last one?
Sure. You want to
go ahead.
Slides? Lynn?
Yeah, I got it. Screen 2. Hopefully this will work. So this one was called the New Mexico Produced Water Economic Socio-Environmental Simulation, not our name. It's a little bit too much. Laboratories like acronyms. Proof of concept. I'm going to skip through this because I know we're running out of time. Okay, so this team, the lab itself had 2 persons on the team who did all the project management. They did a lot of the conceptual stuff. They really didn't do any coding. Well, they did some coding, come to think of it. They managed the stakeholder engagement and most of the data collection. New Mexico State University was a partner on this one. They're a member of a produced water research consortium here in this part of the United States. And they have a complicated Excel model called IDST Fusion, which allows people to look at the costs of treating water based on where did the water come from and where would you like to use the water. So they did some support. They collected a lot of data for us. 2 fellows at the University of New Mexico ran a side project using what's called input-output economic modeling to try to get the economic impact of starting a project in a particular place in the state of New Mexico. And then, of course, these 2 guys were Jake and I. We did all the model building. The key questions: can a model like this help inform the development of science-based decisions? So not just mental models, but the actual science, the hydrology, the chemistry, etc. Can we build an easy-to-use quantitative tool? I'm not so sure. We tried. Can it manage source water selection as well as treatment, application, and disposition? These are hydrologists and economists driving us here. Can we support diverse stakeholders, people with different points of view, looking for different metrics? And can we get to so-called maximum societal and economic benefits? We never did run optimization. We could have, but we never got that far. And the PI on this project also retired from the laboratory. And that essentially ended the project. So there's 1 person here on the modeling. Jake and I, mind's eye, same thing. This one's a bit smaller, 365 variables, 28,000 pieces of data. Notice this, only 4 stocks, right? But also heavily arrayed. Here's a schematic that the PI at the labs put together. The Produced Water Data Portal, which contains an amazing amount of data specific to certain geographies. We sort of clean that up. You do a setup. You do an analysis of the projects that you'd like to initiate, constantly referring to this New Mexico State database. Then show the economic, social, and environmental trade-offs. Also, we link to IMPLAN, which is a input-output piece of software. We were thinking of doing this internally in Studio. We've done it before, but we did it offline and then just brought in the results. Let's see, where am I here? Lost my mouse. Yep, hold on just a second. Got a bit of, okay, on to the model. Jake, it's all yours.
Okay, I'm assuming you can see my screen.
Yep.
Well, this is the introduction screen. Again, it's driven by a mouse. So we go to the map interface. So this one was really driven a lot by where we were as far as location within these 2 counties. This is actually inside PowerSim. This is a GIS application inside PowerSim. And along here is you can look at different layers, right? This is looking at the oil wells in these 2 counties, the SWD or saltwater disposal wells. These are produced water, where it's coming from. So for those of you who don't know, produced water is the water that comes, it's extracted from the earth at the same time that you pull oil and gas out. And it's nasty kind of water, and you have to do something with it. And what they do right now is they typically re-inject it back into the earth. But New Mexico is water starved, and so they want to figure out how to take that produced water, clean it up, and see if they can put it to a good use in that state. So especially in this area in New Mexico, which is hugely water starved. So so then there's gas wells. This is all the gas wells in those two counties. These are the spills. I saw this and I about had a cow. Spills were anything up to like 2 gallons. So a lot of these spills are very, very small, but that's a lot of darn spills. So, and then these are the injection wells that they're using. So, so what you want to do is what we've designed this interface to run this a couple different ways. And in this one, I'm going to show you where we're going to select 3 different areas. Let's say there's area 1. Come on, pick. What are you doing? There's area 1. I'm going to set that as project 1. Project 2 is over here. And I select project 2, and then I'm going to say project 3 is up here, and project 3. And when I select these, you can see over here, it's telling me what township each of these projects are in, lat long, what water basin they're in, what county, and then some data on water in those available in those areas. And then what I do then is I go to the project setup, and in this area, you could tell it. That tells you, it defaults to the water quality that I know of that comes from that GIS location. This water is highly nasty stuff, so it's greater than 100,000 TDS in all those locations. You can select how much water do you want to treat. You can do 5,000 barrels per day, 20,000, and this is how big of a cleanup facility do you want. And then the target industry identifies what the water quality, end-use water quality, has to be driven to be able to use it. So a data center requires drinking water standards. A potash mining facility would require only clean brine, and an irrigation would only require irrigation level water. So these are the standards of, drinking being very high, clean brine being kind of in the middle, and irrigation being like the least amount of cleanup you need. In this case, though, where I picked 3 different locations, I'm going to select the same industry in each case. So I'm going to select where would be the best place if I wanted to site a data center. And so all 3 are going to be the drinking water quality standards. So I'm going to go to the beneficial use screen now. And this kind of breaks down, the flow rates and the capital costs and the trucking costs you need for each of those 3 locations. And it gives you a breakdown of the costs and benefits of each of those. And then we run those through the in-plans, which then gives us kind of an economic impact of those 3 centers. And the one that really matters right here is, if I were to do that data center in each of those locations, what would be my payout? And you can see that location 1 turns out to be the best location for a data center. It has a payback period in about 4 years. And the other 2 are are marginally less than that. And it tells you how many that data center is going to employ, what the income is going to be, the value added, and the tax base from each of those. So that's one way that we can look at this. Look at where would I be the best idea to do a data center or do a different center there. And so you can take 3 places and analyze it for one type of business. You can also come back to the map. I'm going to clear those selections, and I'm going to pick now 1 location, and I'm going to put it into all 3 locations here. So now I've got 1 location, and I'm going to select a different industry in each of those. So I'm going to select potash for this one, and this one I'm going to select, let's say, irrigation. So now I've got the same location, 3 different industries, and I'm going to decide which one of those would be best to site in that location. And so I've done that. So I go to beneficial uses, and this gives me my breakdown of the costs and benefits in terms of that. And then I can look at the in-plant results, and I can see that, wow, potash is just it's much better industry to site there than the data center or the innovation. So it sort of gives you this idea of how these sightings can be done and how you can use that potential water. And we went a little bit further than just economics. We went to freshwater results. and you have to run it out to see that, what the amount of fresh water in those areas are. And then they got way outside of my realm of comfort, and they were looking at human ecological exposures things, and they have a value for each one of these, and you're able to compare, can take a look at these different human ecological variables. And then social justice. We had a social justice expert on the group, and you can look at the different social justice aspects of each of those different projects. So again, it gave you a place to go with a committee or a group of people and sit down and start investigating how you may or may not want to produce water in those areas. And you get past any of the big bickering and fighting, you actually get down to basics and start talking about real things on the ground, right? And so we found a lot of cohesion between these groups and using this interface to debate on what would be the best to do somewhere. Okay, Len, I'll send it back to you real quick.
Okay. Let's see, somebody has a question. I think it's Kareem. Oh, how long does it take? That's a really good question. A lot of it is, none of these were full-time efforts by anyone on the team. Either the Produce Water Collective, the university, the lab, or Jake and I, we were doing other things. And everything was done on Zoom. This team never met together like the other one did, probably because it's in the southeast corner of the state where all the activity took place. So we spent, what, about a year on this project, Jake?
No, a little
Year
over
and a
6
half.
months.
How
A
old?
little over 6 months, just 6 months.
Oh, 6 months. And then
The other one, though, we spent almost full 2 years.
right. Vince Tidwell, who's relatively famous in the energy and water field, retired from the lab. And that essentially ended the project, unfortunately. And you remember how Will asked earlier about transmission lines? There are all kinds of ideas on this one. One was, since you have so much data, why don't you just run the model as an optimizer and choose the best thing to put in every township in the state? You know, what should I put in the state, in this township? Should I put a data center? Should I grow fruit trees? You know, et cetera, et cetera. We never got that far because the project literally ended. But you can see there's some really lofty goals here. If I can find my cursor again. They wanted to present this to the oil and gas industry, and we did a little bit. We wanted to talk to water and economic developers, regulators again, and especially in oil and gas, where you're trying to regulate those spills and injection and all that. In fact, there's a place in that part of the state where the earth is subsiding, and you can no longer drive your car down the road because the earth has sunk. So much has been taken out of the ground. Land managers, public environmental groups. So we find that it becomes the focal point for lots of data that was never put together before. This happens very often. I know all of you have seen that happen. Again, time and patience. Again, this feature issue, right? Oh, you guys got that in? Well, when are you going to start on the next thing? Right? Data management, non-trivial. I mean, my part of my education background is in database design, relational database design. So there's a lot of data work here. And as I just said a minute ago, you get a unique data collection that no one else has. Again, the interface, that GIS-like thing we did, wow, we were so proud of that. And I think the principal investigator at the lab said, "You did what? How did you do that? You can't do that with that software." Yeah. And then I think for this project in particular, Jake and I didn't know how to write this bullet. There's a threshold between, is it SD or a sophisticated calculator? Right. The sponsors all had exposure to SD, and they wanted something SD-like. We didn't have as much stakeholder interaction we didn't have as much mental model to computer model development. And it's just a reminder to us, remember the characteristics of a good problem. Although it did help Jake and I to buy groceries and put gasoline in our car and stuff like that. Right. And
Well,
then,
Graham
yeah.
has a question.
yeah,
And so,
let me go here. I'll put these slides out. Everybody, thank you. Here's some data about us. And if you want to pester us, this is the place to go.
So Graham's asking if we did full water quality
Yeah.
hydrologic modeling. We did not, because we did do a modeling of water being extracted from the oil and gas wells.
Right.
ITDS, IDTS, DST, whatever it was. It did all
IDST.
the analysis on cleanup, and then we took the results from IDTS or whatever it was, and we knew what the clean water volumes coming out and the dirty water went back into the was re-injected back into the saltwater disposal. So, so about the only really water tracking we had was what came out of the wells, what was re-injected back in as contaminant, and what was clean water coming out. So,
Yeah, I see we're just about at time. I guess. Thanks, Joe, for letting us know, and we're glad that we could do this, bail you out a little bit.
Yes, appreciate that. I'm glad we got a good audience for you. So Jake and Len, thank you for presenting. For the audience, thank you for attending. I hope there was insight here. I will continue to promote, and I hope you'll promote also presenters. That's one of the greatest challenges, I think, in running a SIG, is getting candidates to present, prospects to deliver their work and share it with everyone. So please promote that. There's a button on the Systems Dynamic Environmental SIG webpage for volunteering to give a presentation, and I would encourage everyone to use it.
Hey, before you sign off, Will, if you ever see Eric, make sure to say hello.
Well, thanks. I don't see him anymore since he left TU Delft. Also, I still get to the university regularly, but there was some tension with my successor, and so I haven't seen Eric for over 2 years now.
Oh wow! Well, I saw him online at, I forgot which year the conference. 2021 maybe.
Okay, so that's we had a joint PhD that we finished, and then
yeah, that's it.
Yeah,
it's good to see everyone.
Yeah, it was good to see everyone, and yeah, great.
And Joe, good job.
Thanks.
Keep pestering.
Thank you, and appreciate everyone's participation, and hope we can continue to have a strong SIG.
Right.
Thanks, everyone. Have a great rest of the day.
Bye.
Yep. Bye.